Yes. Hello, everyone. So today we are discussing a question based on, we can say, friction in a special scenario. Okay. So when a body enters into a region having friction from a smooth surface, when it enters, then what will be the forces or how you will calculate the work and etc. This kind of question. So let us first look at the question here. So the question reads as a sledge moving over a smooth horizontal surface of ice at a velocity v naught drives out on a horizontal road and comes to a halt as shown in the figure. The sledge has a length L, mass M, and friction between the runners of the sledge and the road is given as mu. Okay, so diagram is given in the question. You can see that. Now they have given you four options. All the four options are different cases, so we can discuss all that. It's like a multiple correct choice, so you have to check all the cases. Okay, so one by one we'll do that. So first, let us draw the diagram. So as per the question, they have given the diagram as this is the ice and the road interface. Here you have the ice this side, and this side you have the road. Okay, and the sledge is right now in this position here. Okay, the length of the sledge. Okay, the length of the sledge is given as v. Okay, coefficient of friction is given as mu naught, and it is just entering, drives out onto that horizontal road with a velocity of v naught. So initially, just before crossing, it is having a velocity of v naught. Okay, fine. Now, what the first part? First part says that no work is done by the friction to switch the sledge from ice to road. Now, this is absolutely wrong. You can understand the moment the sledge enters into the road, the friction comes into play, and the friction will try to oppose the sledge, but definitely there will be some work done by the friction. So, A part is wrong. B part says that the work of half mu mgl will be done against friction while the sledge switches completely onto the road. So that means when the sledge has completely entered into the road, the work done would be half of mu mgl. That's what they're saying. So let us analyze that. So let us say, I'll draw the diagram once again. This time, the sledge has entered into the road a little bit. So let us say up till here you are having ice, and my sledge is now like this. Let us say. So how much of it has already entered? Let us say X amount has already entered, and in a small amount of time, the next few milliseconds, microseconds, picosecond time, very small duration of time, further a dx amount will enter like that. Okay, so during this moment, can we calculate the work? So work done by friction only we are talking, right? Because the question, that option is asking work done by friction. So work done by the friction during the small displacement can be written as the frictional force into the displacement. Okay, frictional force would be acting backward, displacement is acting forward. So yes, negative sign would come. That is okay, but magnitude would be f dx. Okay, so minus of friction force can be written as, because they are given the mu value of a mu in n dx, we can say. Now normal force. See, entire normal force is not responsible for the friction here, because only this much part is actually inside the friction region. The remaining is actually in the ice which was smooth. So let us find out how much of the weight is creating my normal force in this region. Right? So for that we can do one calculation like this. We can say that the total weight of the body, which is mg, is acting on how much length, because as per the question, this length, the total length is L. So can I say mg is acting on a length of L? So the weight acting per unit length is nothing but mg by L. Okay, weight acting per unit length. Now for how much length do I want the weight? I want the weight for x. So now it is nothing but mg by L into x. This is the weight acting in this much part, and that weight would be generating the normal I want. So normal also will be mg by L times x. Now substitute that value here, and you'll be getting it as minus of mu mg by L x dx. This is the work done by friction for that small displacement. Now I can find out the total work done. Total work done for the entire displacement of length L, that is completely entering into the sledge, completely entering into the road. For that I can integrate it. Mu m g by L, everything is constant. Integration of x dx. Limit is going from x started from 0 and x will become last L. So this will give me L square by 2, 1 L can be cancelled, and finally I'll be getting minus of half mu mgl. This is the work done by the friction. So work done against the friction would be a positive value. Okay, and that's what the question is saying. The second option reads that a work of half mu mgl is done against friction while the sledge switches completely onto the road. Okay, so that part is correct. B is correct. Let us look at C. C part says that the distance covered by the sledge on the road is, because the sledge will finally come to a rest. Yes, in the question they are saying on the horizontal road and it comes to a halt. Finally, halt means finally it will come to stop. So distance covered by the sledge on the road would be how much? Okay, so that we can find out by what? Initially it had a kinetic energy, finally it is coming to stop. So change in kinetic energy we will be getting. So we can write it as W net equals to change in kinetic energy. We are using the concept of work energy theorem. This would be much more easier, right, to solve. Now, work is actually done by friction only, but I'm going to divide this work into two parts. One, the work done by friction while entering, and then work done by the friction once it has completely entered. So two parts I have divided. That is equal to change in kinetic energy. That change is nothing but final minus initial. The final kinetic energy being 0, initial kinetic energy is half into m into v naught square. Like that we can write. Now work done by the friction while entering, just now only we found out, this is what will be the first work done, right? So I can call it as minus of half mu mgl plus work done by the friction once it has entered. Once it has completely entered, we can write the friction force as mu into mg completely, because the body has completely entered. So now the normal force will be completely that mg value into whatever displacement it is doing after entering. Okay, so after entering, it has further gone some distance y x, or let us call it as d. Okay, d amount of distance it has traveled after completely entering before it comes to stop. So that is minus of half m v naught square. This work done by the friction should be also a negative value, right? Because friction would be in the opposite direction to displacement. So all the minuses can be cancelled, all the mass can be cancelled, and from here finally I'll be getting the d value as v naught square by 2g. Am I right? V naught square by 2g. I think I'll also get a mu value, 2 mu g. Okay, let me not skip the step, because I'm skipping the steps. I may write something wrong here. So let us not skip the step. Directly I can write it as mu mgd is equals to half m v naught square and minus half mu mgl. This is what I get. Now I'll do that. Divide the entire thing by mu mg. Okay, so this would give me m gets cancelled, v naught square by 2 mu g minus, when I divide by mu mg, that gone, what remains is L by 2. So this is my equation I'm getting. D equals to v square by 2 mu g minus L by 2. This is a distance traveled by the cart once it has entered before it is coming to stop. So the C part says the distance covered by the sledge on the road is v naught square by 2 mu g minus L by 2. Correct. Okay. Next part. The total distance moved by the sledge before stopping is, see, total distance moved by the sledge before stopping. So initially it covered a distance of L to enter into the road. After entering into the road, it further covered this much distance before coming to stop. So the total distance covered by the sledge, capital D, is nothing but L covered by while entering and plus D covered after entering. So if I add this L plus D, it will basically become L by 2 plus V naught square by 2 mu g. And what is the last option they are saying? The total distance moved by the sledge before stopping is V naught square by 2 mu g plus L by 2. Yes. So based on this, we'll understand that all the three options that they have given is correct. Now, what is the important thing about this question? The important thing is that finding the work done while entering. Okay. So this students might understand, try to figure it out, make sure that this concept you understand. Whenever this type of question comes, the friction is continuously a varying force, because as I enter more and more into the road, more and more friction would come. So directly I cannot find the friction, I'll have to integrate it and get it. Whereas once the body has completely entered, the friction remains constant. So while finding that work done, it was pretty easy, just multiply force with displacement. Okay, so we'll stop here. Thank you.